Hi, my name is Kota Saito from Caltech. Today, I'd like to talk about my joint paper with Haruki Kono and Alec Sandroni. Consider a group of individuals making a choice among finite set of alternatives. We observe percentage of people who choose each alternative X from its subset T of X. For example, if X consists of 4 alternatives, we observe choice frequency of alternative A out of ABCD, choice frequency of A out of ABC, and so on. This type of data set is very common in economics. For example, market share data. One fundamental model to describe this kind of data set is random utility model. The model simply specifies a distribution of possible rankings over X. So for example, if there are 4 alternatives, say 10% of individuals have a ranking A, B, C, D, A is the best alternative and the B is the second and so on. No one has ranking A, B, D, C and so on. Furman provides a classical fundamental results. He provides a necessary and sufficient condition on the data under which choice frequency is consistent with a random utility model. That is, there exists a probability distribution mu over ranking such that choice frequency of X out of choice set T coincide with the measure of a ranking such that X is the best alternative among D. However, this very nice results by Furman requires strong observability condition on the data set. He requires that we know choice frequency rho dx of any alternative X from any subset D of X. Okay. However, such assumption are often violated in reality. Let's consider a couple of examples. Transportation example. Let's say X consists of 4 transportation methods: bus, train, walk, and drive. The government may be able to estimate the market share of public transportation, bus or train, based on revenues, bus company or train companies. However, it may be difficult for the government to know whether a passenger drives or walks unless the government conducts a survey. So in this situation, choice frequency of walk and drive may not be observable. There are many other examples. For example, market share of private companies. One definition of market share is percentage of company's total sales divided by the market's total sales. However, private companies sometimes do not disclose their financial information, including total sales. So market share of private companies may not be observable. Another example, school choice with private schools. Students submit their rankings among public schools, but not private schools. Government can know choice frequency of private public schools, but not private school. Okay. There are many examples like this, and our question in the paper is, in this setup of missing data, what is a necessary and sufficient condition on the observable data under which law is consistent with random utility model? This is very basic and simple, important question. However, it is known that obtaining a tight, necessary, and sufficient condition is very hard for the case of incomplete data set in general. Okay. Whenever Furman's condition, strong observability conditions violated, it is known that it's a very hard problem. For example, when we observe choice frequencies only for binary choice sets, how to obtain tight, necessary, and sufficient condition has been an open question since 1890s. Despite continuous effort in mathematics, discrete mathematics, mathematical psychology, and theoretical economics. And the tight characterization is known only for the case when the number of all alternatives is less than 8. okay? So it's very difficult problem, but however, we found a tight, necessary, and sufficient condition for this setup of missing data. Okay, so that's what we did. So now let's formalize this problem. Okay, so remember the example of transportation methods and private companies and then school choice with private schools. In all examples, we have a finite set of alternatives. And some of them is unobservable. We denote it by X star. Okay? We assume that the choice frequencies of elements of X star are not observable, even if a choice set includes the alternatives. Calligraphic D is a set of choice sets. Okay? In this presentation, assume D contains all subsets of X, but in the paper, we simply assume that calligraphic D is an upper set. Okay, upper set is a mathematical term, just meaning that if calligraphic D contains D, then all its upper set, all set containing D also belongs to its calligraphic D. Okay. Couple of notations. M is a pair of D and X such that X is in D. Okay, just to make notation simple. M star is unobservable pairs. It's pair of D and X such that either X is unobservable, meaning X is in X star, or choice set D is not available. Okay, so choice frequencies on dx belongs to M star is not observable. Okay. Note that this doesn't mean we do not know anything about choice frequencies of X star. If there is only one unobservable alternative in the choice set, just by using the fact that the sum of probabilities must be summed up to 1, we can calculate the choice frequency of the alternative. Okay? Formal definition, a vector is called an incomplete data set if for any D in calligraphic D, if D doesn't contain any unobservable, it must be summed up to 1 because it's probabilities. Otherwise, if it contains unobservable, it must be summed up to less than 1. Okay, because some of the probability is missing. Okay, so now let's go back to transportation example and let's see how this framework works. The government may be able to estimate the market share of public transportation methods, bus or train, based on the revenues. However, it may be difficult to know how many people walk or drive. Okay. In this example, there are 4 underlying transportation methods: bus, train, walk, and drive. However, walk and drive choice frequency is not observable. So therefore, X star consists of the 2 elements. And we assume that depending on location of homes, some options are not available. Okay, so simply because someone's home is too far away from bus station or train station. For example, some people may only have a choice of taking a walk if he or she doesn't have a drive, and if he or his house is too far away from bus station or a train station. Okay, and so on. So now let's going back to the definition. And then again, here is the formal definition of random utility rationalization. L is the set of rankings on X. An incomplete data set law is random utility rationalizable if there exists a probability measure of a ranking such that for any observable pair D and X, choice frequency law dx coincide with the measure of a ranking such that X is best alternative in D. Very simple. Okay. Okay, before going to our results, let me remind you the famous results by Farman and Bloch-Marshak polynomial. Assuming that all alternative is observable, meaning X star is empty set, and we observe all choice sets, Farman showed that following two statements are equivalent. Rho is random utility rationalizable if and only if a polynomial k defined by this way is non-negative. Okay? This polynomial is called Bloch-Marshak polynomial. Okay? K rho dx is sum of choice frequency of alternative x across superset of D. Okay? This is a summation over sets, including D and its upper set, with alternating sign. Okay, so let's take a look at the example. If D contains all alternatives but one, then K rho dx is simply first adding rho dx, okay, and minusing rho xx. Okay, so here, okay, when I'm summing up superset of D, there's only one superset, that is X, and an alternating sign, -1, to the power of elements contained by E, but not D. So in this case, there's only one element, so that's why we have a -1, okay? And we have, here 1, because, when E is D itself, the power is 0, okay? If D contains all elements but 2, so then rho dx minus rho d union yx and minus rho d union zx plus rho xx. Okay? That polynomial, simple to calculate, is called Bloch-Marshak polynomial. Okay? And what Farman showed is that random utility rationalizability is equivalent to the condition that all Bloch-Marshak polynomial is non-negative. Note that in our setup, we can't calculate some Bloch-Marshak polynomial, but we can calculate some of them. Actually, we can calculate Bloch-Marshak if and only if the pair dx does not belong to M star. Okay. Okay, so now I'm going to state our theorem. So in order to state the theorem, I need to review just one concept. A collection C of subsets of X is called test collection if there exists a non-empty set A of observable alternatives and a collection of sets of unobservable alternatives such that the collection C can be written as a union of A and then elements of it. Okay? And then this collection must be an upper set. Okay? So that's the notion of test collection. Okay. Okay. So what is important is that then it's simple to define, and then given the setup, it's simple to specify what is the test collection. Okay. Now here is the result. An incomplete data set rho is random utility rationalizable if and only if we have two conditions. Okay, one, all Bloch-Marshak polynomial that can be calculated is non-negative. Okay, again, as I said, some of Bloch-Marshak can be calculated. Okay, so for such Bloch-Marshak, I want that to be non-negative. Now, here is the new condition. For any test collection, which I defined in the previous slides clearly, sum of Bloch-Marshak minus sum of some other Bloch-Marshak is non-negative. Okay? And such inequality condition is defined for each test collection. That's the condition. Okay? Notice that, again, as I said, Bloch-Marshak in the first condition is computable because this is calculated for any dx which doesn't belong to M star. And also it's easy to see that Bloch-Marshak polynomial appearing on the second condition is computable because of the definition of test collection. Okay, so here I found that then there's one typo here, y here in this second term. must be observable alternative. So Y should not belong to X star. Okay. Condition 2 has very intuitive, clear meaning based on network flow theory, which I'm going to explain in another video. Okay. So that's statement A. Our emphasis is this second statement. For any inequality condition in 1 or 2, there exists an incomplete data set that violates the particular condition but satisfies all the other inequality conditions 1 and 2. This means that not only our theorem provides a necessary and sufficient condition, but also it is minimal and tight in the sense of this statement. Okay. It is known that the set of random utility model is a polytope in some space, and our condition specifies all facet-defining inequalities of the polytope. Okay. In general, it is known to obtaining such a result is very hard. Okay. Implication. In empirical industrial organization literature, okay, use of random utility model is everywhere. And in fact, some choice frequency is unobservable, like a transportation example. In such a case, researchers sometimes put all unobservable alternatives together, like an outside option, and treat them as one big alternative called outside option, even when the analyst knows which elements are in X star. Notice that when there's only one outside option, right, we can calculate the choice frequency of such alternatives. Okay. Theorem 1 implies that this naive approach may ignore some feature of random utility model. More precisely, it doesn't consider condition 2 in theorem 1. Okay. Because naive approach boils down to Fuhrman's characterization, it just requires non-negativity of Bloch-Marshak polynomials. Our contribution, high-level conceptual contribution, is to demonstrate this difference clearly by providing a minimal set of tight testable conditions for observable choice probabilities to be consistent with the random utility model. In the paper, we proved the result using network flow theory. And one message which we think is important is to test random utility theory, not just proving. Network flow approach is more efficient computationally than the standard linear programming approach because of the network flow structure. That gives us a specific property of a matrix that makes matrix as an incident matrix. Okay? That makes computation more efficient. As an application, we obtained a bound for missing choice frequencies. Remember transportation example. Okay? Government may want to know how many people actually using a car to go to their office, right? Okay, so, but however, you know, the data set consists of choice frequencies of using bus and train, how to get a reasonable bound for unobservable choice frequencies. We provide an algorithm based on our theorem. Okay? Moreover, we apply these algorithms to a real data set, and then we obtain the bound for choice frequencies. Okay? And then we compare our method with the naive approach, in which we put all unobservable as one big outside option. Okay? So that's what we did in the paper, and I'm running out of my time, so I'm going to post my video based on, in my webpage. So if you are interested in, take a look at it. So the approach, again, is based on network flow theory, and it has a very intuitive explanation. Okay, so thank you very much, and I hope you can take a look at the continuation video in my page. Thank you.